Okay, welcome back everybody. This session has two talks. First one will be given by Professor Nagaosa from University of Tokyo. Tell us about topological aspects of proximity effects.
Thank you, Mr. Chairman. So first of all, let me thank the organizers, even though I'm one of the organizers, but just a nominal. So Taikai and Fujin for this tremendous effort to organize this workshop. So today I would like to talk about some new stuff related to the proximity effect. So let me introduce my two collaborators. So one is Bon Jung-yang at RIKEN. Actually, he was a student of Jae-jung Yu and went to Yeonbaek place and come to my place. So this is a very nice, excellent postdoc in my group. And the second one is Bahrami-san. He is Iranian. And this is a Korean and Iranian-Japan collaboration. So quite perfectly fits the scheme of APW. So that's why I present this talk today. Okay, so these are some generic ideas. We are interested in the interface or some proximity effect. So putting the completely different system together, and something happens at the interface. So sometimes if you put the topological and non-topological stuff, and sometimes topological and topological stuff, and sometimes non-topological stuff. Right? So there are many, many combinations. And interestingly, even if you put the non-topological stuff, something topological could appear. So that will happen. And also, there are a combination of the one-dimensional and two-dimensional proximity effect. This is well known for the appearance of the Majorana fermions at the edge of the quantum wire put on the superconducting systems and so on. So there are a variety of combinations of systems. And today, I would like to focus on this number one. So the bound states protected by the topology. So I will explain you in the following slides. And if the time allows, I will touch on briefly the proximity-induced Majorana bound state on top of the superconducting systems. Okay. So let me start by talking about the very simple stuff. Probably this talk is the simplest in this workshop. The content is very, very elementary. So I'm interested in the bound state in solids. And this bound state is, for example, represented by this donor or acceptor levels. So in order to have a localized states in solid, actually that state should be inside the gap, right? So here is a continuum of density of states called Bloch states, right? And this conduction band and valence bands. And usually these localized states should appear in the gap. And the localization length, lambda, is related to this bound state energy measured from the bottom of the conduction band, for example. So this is very simple physics. But now, even if you have the continuum of density of states, you could have localization. So this is the famous Anderson localization. But here the concept of the mobility edge has been proposed by Mott. So the bottom line is the following. If you have some localized states and the extended states coexist at the same energy, it is forbidden. So the reason is that hybridization with the extended states prohibits the localization. So that means there should be some clear energy which separates the localized states and the extended states, because the localized states cannot exist in the middle of these extended states, right? So that's why some critical energy should appear, which is so-called mobility edge. So this is a bottom line of this Mott proposal. Okay. So now everybody knows about this scaling theory of localizations, and you can define the beta function. If you change the sample size, the dimensionless conductance scales in this way. And the beta function is quite a universal and depends on the dimensionality and also the universality classes, namely the symmetry of the systems. You can have this beta function. So now, in the case of orthogonal and unitary class, so 2D system is always localized. And for the 3D system, you have a critical point, which separates the metallic state and the insulating state. So the positive beta value means you have going to the metallic states. So these are basics and described by this review paper. But now, sometimes the topology matters. Okay, so the one example is quantum Hall systems. So here is Landau levels broadened by the disorder potentials. And naively, you have a two-dimensional system and the unitary class. So you have expected that all the states are localized. But if all the states are localized, sigma xy should be 0. So then you need another parameter, namely the two-parameter scaling theory has been developed. And the sigma xx and sigma xy is controlling scaling parameters. And that concluded that there appears some extended states in the middle of these Landau levels. So then this extended state carry the whole current, and sigma xy is quantized. So this topology affects the localization problem. And recently, lots of attention has been focused on the absence of the localization on the surface states of the three-dimensional topological insulator. So this is one example by Nomura and Shinsei Ryu. And if you map the localization problem into the nonlinear sigma model, there appears a topological term, which gives you the sign depending on some topological number. You have a positive or negative contribution to this partition function. So this modifies the beta function quite a lot. So this is a conventional symplectic class, and you have an anti-weak localization and becomes insulator at some critical value of the conductance. But in the presence of this topological term corresponding to this surface state, your beta function is always positive. So that means localization is absent as long as you respect the time reversal symmetry. So this is one very interesting example where the topology really dictates the extended states. So up to now, we talked about the topological protection of the extended states. So the main reason is that this, for example, this Chan number represents the response of the twist of the boundary condition and contributed only by the extended states. The localized states cannot respond to the twist of the boundary condition. So in other words, the topological number or invariance protects the extended states. The only possibility is that the pair annihilations of the extended states of topological number occurs to destroy these extended states. So this is sort of a common wisdom. But now let me ask the opposite questions. The question is there any topological protection of the localized states or bound state? So this is the new question I want to pose. So the situation is the following. Here is a two-dimensional quantum Hall insulator or two-dimensional quantum Hall systems. And here you have a substrate. So this is a very usual situation, right? So usually you can forget about this insulating substrate and focus on these two-dimensional systems. But if you are careful enough, there is a band structure for this three-dimensional insulating system given by this. And if I attach this 2D system on top of this 3D insulator, there are two possibilities. So the one is this two-dimensional state is slightly hybridized, but still exponentially decaying. So this I call the localization along the z direction, or the bound state near the top layer. The other possibility is because you have this block wave in three-dimensional systems, your system will be hybridized to be extended along the z direction. So these are two possibilities. So my naive thinking is the following. This is a relative relationship between the three-dimensional density of states and the two-dimensional density of states. When the two-dimensional state is within the gap of the three-dimensional density of states, then you expect this, right? Because this is localized along the z direction. But you can also think about the situation that your 2D states are completely buried in the three-dimensional density of states. Then expectation is that you have this hybridization and extended, right? Because right, there could be no bound state in the middle of the three-dimensional continuum because these are extended states.
Excuse me, but here one is negative the gap, another is positive gap. When they put together, I mean, you have two gaps, right? One is positive, another is negative.
What do you mean by negative?
Right.
You're talking about the sign change of the mass?
I mean, the quantum Hall insulators has a negative gap, and your substrate has a positive gap.
Yeah.
So when put them together, they can forms an interface.
Yeah, I'll back to your point. Okay, so this is a question. And another question is, for the two-dimensional case, you have a edge channel, chiral edge channel. Whether this chiral edge channel is still localized near the top layer or also extended. So these are the questions I want to pose. Okay, to study that problem, I take this Haldane model and for the quantum Hall effect. So this model shows quantized sigma xy without lambda level formations. So you have a well-defined band structure, but the trick is the following. So in addition to the conventional nearest neighbor hopping, you have a complex second nearest neighbor hopping. So that produces some flux penetrating the loops, which can be defined in this way. So in the K space, you open the gap at the K point and K prime point. As you know, without this next nearest neighbor hopping, you have graphene's massless Dirac fermion here. But this term, which breaks the time reversal symmetry because of the complexity of the hopping amplitude, you open the gap at the K point and the K prime point. And the sign of the mass for the K and K prime could be the same. So in that case, you have sigma xy quantized. And you have a quantized Hall effect without lambda level formation. So this is a famous model by Haldane. So I put that Haldane model here on the top. And also, I can put Haldane models and put the transfer integral along the d direction. But I tune the parameter to make this substrate to be trivial. Namely, the sign of the mass is different between the K and the K prime point. Then this system becomes trivial. But this system is quantum Hall systems. So then
the lower part will have a charge density.
Yeah, sort of. Yeah. So you have up and down.
Nitride,
Yeah. Something like that. So it is, but I also introduced transfer integral. So that is the directional dispersion and form the bands. But you can think about the two situations, this case and this case, by tuning the band gap in the substrate. So there's a setup of the problem. Okay, so here is the result. This is a little bit complex, but let me explain. So this one is a three-dimensional density of states, and this is a two-dimensional dispersion. I put kx to be fixed, and ky to be fixed, and I change the kx. So this is situation, you have a completely, your 2D states are completely within the gap. So as you expect, all the states are exponentially decaying. And if you go to the deep in the substrate, so these 2D states disappears, right? So these are very natural. And this is the magnitude of the probability density at the top. So the red one is very high density. Even though this is blue, this means 0.94. Most of the states are localized near the top. But you can also think about the situation where part of the K-space, your 2D states are buried in the three-dimensional density of states. And correspondingly, only in this K regions, you have exponential localizations of the 2D states. But now the non-trivial case is these 2D states are completely buried, right? And still, you could have the exponential decay at some particular K point. Here is Z dependence. I mean the layer dependence of the amplitude of the wave function. So this is a completely exponential localized case, and this is the extended case. So you have a tail. Of course, you have a maximum weight at the top layer, but it doesn't decay. So this is a situation like that. But in this hotspot, hotspot, so your state is exponentially decaying. This is not totally decoupled from the 3D substrate. It is somehow interacting with 3D states, but exponentially localized. So this is a sort of a surprise to us. Then the next question, why these states are exponentially localized in spite of the hybridization with 3D density of states? Okay, here is our explanation. So this is the only slide with equations in my talk. There are a lot of equations, but very simple, because this is basically the non-interacting problem. But we have the two-dimensional states and three-dimensional states and the hybridization between the two. So basically, this is a 2x2 Hamiltonian, and you can integrate over the three-dimensional states to derive the effective Green's function for the two-dimensional states. Actually, to discuss the topology of the states, sometimes the block wave function cannot be defined, and you should go to the Green's function. And actually, I learned from Su-chan at the Nagoya conference to discuss this topological nature in terms of the eigenstates of the Green's function. So the same idea could apply here. So then you can integrate over these three-dimensional states. So the Green's function has a self-energy, right? So this is coming from the integration over the three-dimensional substrate. Then the structure of the Green's function is given by this. Here I focus on the imaginary part of the Green's function. So the idea is the following. Once you have the delta function of peak for the Green's function, that means localized states along the z direction. Once you have a hybridization, you have a usual resonance peak, right? So then the question is the imaginary part is 0 or not? So that is a criterion for the localization problem along the z direction. And in this problem, we have a kx and ky are still well defined. So then for each kx and ky, you can define this Green's function as a function of omega, right? Then you can look at the structure of the pole. So it turned out this Green's function self-energy is represented by some unit vector called A vector, which is given by this. Because this is a 2x2 Hamiltonian, you can express the Hamiltonian in terms of the Pauli matrices, which is tau x, tau y, tau z. And this H vector is coming from the three-dimensional band structure. And this small h vector is coming from the two-dimensional band structure. And then the Chern number is related to this small h and also small a, because the 3D state has topologically trivial. So that means the Skyrmion number in small a space is 0. So in the kx and ky space, the a doesn't wrap. I mean, fermion number is 0. But for the small h, because the Chern number is finite, you have a finite fermion number. So that means at some k point, the direction of the small h and direction of the small a should coincide or the opposite direction. So they are parallel to each other. So at that special k point, your imaginary part goes to 0, and you have a delta functional pole. So that means you need a localization, bound state should be there. So this is a logic for the 2x2 Hamiltonian. So in some sense, in that sense, the topology protects the bound state. So this is a proposal. And let's go to the H channels. Once you have localized states, but most of the kx and ky point, you have an extended state. So the question is, can you still have the localized H channel near the top of the systems? So the answer is yes. So we carefully analyze the z dependence of the H channel wave function, and it is exponentially localized, right? So then,
what's the localization name?
Basically determined by the inverse of the gap size. Okay. So, but actually, the referee was not satisfied by this, and he wants 4-band models because our analysis was based on the 2x2 Hamiltonian. Then why don't you go to the 4-band models? And we studied very many cases, and this does not give you much information. Then let me explain what we have been doing. So this red one means you have a large amplitude on the top layer, and the blue one is a small amplitude. Okay, so the one case is the following. So you have, this is a Chern number for each of the 4 bands measured from the top. So the +1, -1, 0, 0. So I just focus on this upper 2 bands. These are 2-dimensional, and these are 3-dimensional bands. So now these 2 states are completely buried in the same 3-dimensional continuum, right? So then let me ask, what happens to the these 2D bulk states? And actually it turned out, even though we do not have any gap between the 2-dimensional states, namely the 3-dimensional continuum covers all these energy regions, but this 2-dimensional bound state survives. You can see by numerics. But interestingly, the H channel which connects this upper and lower 2-dimensional states is not localized. Then it is extended. So even though you have a Chern number plus and minus, and you have a z-dimensional, bound state along the z direction for the bulk states, then the edge state is not localized. So the localization of the edge state is due to the gap. But the localization of the bulk state is not due to the gap. So there is a clear difference between the two. And also, we considered several possible combinations of the Chern numbers for each of the 4 bands. The generic principle is that Chern number protects the 2D bulk states bounded near the top layer, and the edge channel is localized within the gap. So this principle always applies. But now let me go to the quantum spin Hall systems. So we first start with this combination. So this is spin up, spin down, and spin up, spin down. So if you have the conservation of the SZ, then this is just 2 copies of finite Chern number systems, right? So then the same criterion applies. But now I want to mix this spin up and spin down by some spin orbit interaction. Then what happens? So there are 2 cases. So when the 3-dimensional substrate is spin polarized, namely the 2-band models, then this, even though you mixed up this spin up and spin down, the bound state are still protected. So your exponential decaying state survives. But now I want to keep the time reversal symmetry by making the substrate system also for the 4-band model and keeping the time reversal symmetry, then this 2-dimensional bound state disappears. So all the states becomes hybridized. So it seems to me that this Z2 topological number does not protect the bound state. There is some clear difference between the Chan number and Z2 number for this topological protection. And also, we are back to the 2-band models and make the Chan number twice, so plus and minus 2. So in this case, the number of 2D bound state increases. So it is natural because you wrap your H vector twice. Then you have many chances to cross this small a vector. So then this is one case. And the other case is we can also make the 3-dimensional substrate to be topological. You have the sigma yz and zx and sigma xy. So you can define the 3 set of the Chan numbers for the 3D substrate. And we have 0, 0, 1. You have just a stack of the 2-dimensional quantum systems. And this has been discussed by Leon Barents and Matthew Fisher a long time ago. And you have surface chiral H channels, which is 2D. And you have no localization in this case. But also, you can make this 1, 0, 0 combination. But we also could not find any bound state in this case. So this is all what I have. And then at the last part of my talk, let me explain why I was motivated by this problem and some possible candidate to realize this scenario. So which is a pyrochlor antiferromagnet. So this has been discussed by Ashbin and his collaborators. And actually, this system has a 4-in, 4-out spin structure. And depends on the strength of the Coulombic interaction. There are many interesting phases. But the real material seems to belong to this strong coupling regime where you have a trivial Mott insulator because of the long-range ordering. But the bulk, you have a trivial. But if you look at the surface of this system along the 1, 1, 1 direction, so you form the Kagome lattice. And the spin structure of this Kagome lattice is like that. So you have some non-collinear or non-coplanar spin structure that leads to the distribution of the flux in this way. So this 2-dimensional Kagome system could be quantum Hall systems because of this flux distribution. Then this is the situation at the top. On the surface, you have quantum Hall systems, but the bulk, you have a trivial insulator. So this could be the possible realizations of the scenario I just described. Okay, let me summarize. So I discussed about the topological protection of the bound states against the hybridization in the continuum of the extended states. And the Chan number guarantees the points in K space. And you have just a major 0, discrete K point. And if you are slightly away from that K point, the system becomes delocalized. So, but that was I mean, protected by the topological number, right? And then the edge channel is localized near the top layer as long as it is within the bulk gap. So lastly, the Z2 number seems not to protect the bound state in contrast to the Chan number. So I just gave you our numerical results and some considerations, but we do not have theory for this. So there must be some rigorous theoretical framework to describe this hybridization problem. So thank you very much for your attention.
Is this protection of the localized state, is it robust to disorder in the plane?
Yeah, that's the most interesting problem we are now working on. But because we need to treat these 3-dimensional systems, the sample size is not so large. But that is the most interesting question. Our first naive expectation is that you have some extended state in the 2D. So this extended state is localized along the z direction and smoothly continue to this H channel. You are suspicious supporter. Yeah, let's talk about that. Yeah, this other problem should be quite interesting. Right?
So have you tried if the bulk is a superfluid, so in principle, you repeat the program where the inside, I mean.
Yeah, you mean Beaulieu-Dugan, you mean?
Sorry?
You are talking about the superconducting?
So when you replace the bulk as a superconductor.
Superconductor, yeah.
So do you get the same protection and then you lock in certain energy? You would probably have more properties.
Yeah. Yeah, that's an interesting question, but we haven't studied this Beaulieu-Dugan.
Okay.
I just have a comment about protection of extended state.
Yeah.
Extended state in the quantum Hall effect are for the critical state. There is difference between usually extended state in a metal and extended state in the sense of the quantum Hall effect.
Mm-hmm.
I mean, you can see it by multifractal analysis and so on.
Mm-hmm.
But they are somehow different. Now, the other question, maybe it's related to this, but I understand that you studied the localization of the edge states
Yes.
in one direction.
Yeah.
Do you have an example where you protect bound states in all three dimensions?
That's the real localized states.
Yes.
Yeah. Actually, as far as we studied, we don't. Yeah, I think in that case you need a gap. The state should be within the gap, I think.
Okay, without
Okay.
further questions.